Hello everyone. Today we're going to discuss about the magnetism. That will be your second section of the unit 4. So you remember that the section number 1 in unit 4, last section, we discussed about the electricity, right? But any devices that you are using in your real life is combination of electricity and magnetism, because the electricity is not enough for us to get the very good device that perform better. So that means we need the information about the magnetism for the development of the new technology. So everybody have seen the magnets, right? So magnets, you know that you can stick into your refrigerator or some kind of like your car door or somewhere that you can stick them to the metals. So now why this is happening? So that's the part that we're going to discuss on this section. And in your textbook, this will be actually chapter 22 and the 23 together. Again, there are a lot of information under these two chapters, but we're going to discuss very conceptually to get an understanding and get an why we need the magnetism phenomena in your technology or devices that you use in your medical instruments and you using in other devices, why we need to know magnetism, right? So now in this section, let me share my PowerPoint first. So under this section, I am planning to discuss about basically first the magnets. Magnets, everybody have seen this kind of things, right? You can stick into the your refrigerator door. But why they are sticking together to the door, and we're going to discuss that, right? And then we're going to move into the other source of magnetism, because magnets can create the magnetic kind of field or the magnetic force, but what are the other methods that we can use to create the those kind of fields? And next we're going to move into some kind of idea that to get why when you have two wires close to each other, when they carry the current in one direction, are they going to attract each other or are they going to repel each other? We're going to discuss that concept a little more. And also then we're going to move into the induced voltage. That means that we can induce, or we have a new devices like induction coils and those things that we can induce the voltage even without the power source. So that's we call it as induce, and we're going to talk about the Faraday's law under that. So now magnets should have kind of we call it as poles. So magnet can have north and south pole, right? So similar to the electricity, you remember that electric part, we discussed about the positive and negative charges. Similar to that, I have north and south, but poles, not exactly charges, right? So north and south poles. So north and north will repel each other as positive repel, and south going to be repel. And but if you have north and south together, they're going to attract each other, right? So that concept, you guys know that if I take the two magnets, you can see it in here. I have a red side in here, we'll say it is north, right? So when I try to bring these two together, although I push it harder and harder, I cannot bring them together. This is the least closest point that I can move. I cannot bring them together because there is a pause, there is a field in between these two that will repel each other, right? But if I bring the south and the north, they're going to attract each other. I don't even want to push it. When I keep it in here, it will go together and it stick together, right? So that's the basically call it as poles. Those are poles, right? So now what you can do is you can try to cut this magnet into pieces, but you never can separate this north and south. It is color you can separate, but your magnet, if it is a magnet, you are not able to separate the north and south, whichever part that you have should have a north and south, both poles on that piece. And so now magnetic field have the kind of pattern. So that is called it as magnetic field lines, similar to electric field lines. Magnetism also have magnetic field lines. That's why that these two are not allow me to bring them together, or why these two are bringing together, because there is a field in between these poles, right? So now the magnetic direction or the field direction will be able to measure by using compass. If you have seen the compass, you're going to see that in your laboratory class. Compass is a kind of circular kind of object, but there is a needle inside. One is red side and the other one is blue side, but there is a needle. What happens when you bring that closer to the magnet, this needle going to point in this direction. So that pointing direction you will see is the direction of your magnetic field lines. If this one is north, if this one is south, that means your magnetic field direction that you will see this way. So that direction is the magnetic field line direction. So I have a diagram in here. So you remember that in electricity, we call it as starting from positive and ending with negative. But it is very important that magnetism does not have that kind of concept. Magnetic field lines does not have starting and ending points. They are always circular pattern. So that means even if I start with the here north and it will go from north to south, but still there is a magnetic field inside this magnet, right? They are circular patterns. And where this magnetism actually coming from? There is two parts, two components important for that. You know that when I have the kind of atom, there is an electron sitting outside. This electron is orbiting around the nucleus. So because of this orbital motion, there is a revolution of this electron. There is a kind of magnetism created, or there is a kind of momentum that will create. We call it as angular momentum because of that, because of this rotation. And in addition to that, this electron rotate itself. That's how it will go around. It will rotate itself and going around the nucleus, right? So because of this spinning of electron itself also will affect the magnetic field. So especially that spinning is very important. If you have one electron is spinning upward direction and second electron also is spinning upward direction, then your magnetism will create on the same direction. But if you have one spinning this way, other one is spinning this way, then you have up and down, then your magnetism will be lower. Right, so that's how the magnets you have, we can create antiferromagnets, ferromagnets, paramagnets, those kind of things will define because of this direction of the electron movement. So now Earth itself, there is a huge magnet on the Earth center. So that magnet has the north and south, but don't confuse that north and south is not geographic north and south. Geographic north and south are different things. You can see it in here. This is the geographic north label, but this is actually south pole of the magnet. Okay, so now this magnet in the middle, actually it's saying that it is observed that this is changing with the time. So around 300,000, after 300,000 years, this magnet going to switch north and south. Basically, it's totally turn in 180 degrees. And so now we have kind of understanding. If I have north and south, there is a kind of attraction between these two, right? So that's attraction because there is a magnetic field created in between these two, right? So now another way you can think, if you have a south magnet at the top and north magnet at the bottom, then magnetic field lines going from north to south direction. Because of that, I can levitate very small object in between these two. If my gravity is smaller than the magnetic field it create upward, then I can levitate this small mass object. Okay. And so magnets definitely can create magnetic field. So we know it. So now in addition to that, magnetic field will be able to create by using current carrying wire. If I have a wire that will carry the current, we'll say this is a wire, it is carrying the current upward direction, right? So now when it carries the current upward direction, if you bring the compass to this point, you're going to see your compass needle pointing in that way. If you bring the compass in front of that, you're going to see this way. So backward this way, right? So because of this magnetism create around this wire because of the current of this wire. So that's why I have these compass needles. You can see that if I have a current in the direction, this is the needle pointing, that's where the magnetic fields is, right? But it's very important that when you have the very close to the your wire, magnetic field is very strong. Here I have a very stronger magnetic field. I'm going to draw a big circle with the cross because I have magnetic field going inward direction. These two symbols have meaning actually. This one is, we call it as inward. That means third direction that I'm not able to draw in the screen, right? And this one we call it as outward direction, inward and outward. So now here I have an inward direction magnetic field, but when it go further away, it is getting weaker and weaker because there is a connection to the current, and when you go further away from the current wire, magnetic field will be weaker, right? So now even the coil, you can use same concept, right? So now where this direction coming from? That direction actually coming from, we can find by using your right hand rule. So now it is very important that when I do the recording, you will see I am lifting my right hand. Actually, this is my right hand, but you are seeing the mirror, right? Make sure that you follow those when you do the those kind of problems, because it is not able to show to you my right is your right in the screen, right? So now first thing is, if I have the current in here going upward direction, then you're going to take your right hand, right hand only we're going to use, and then your thumb is going to point to the direction of the current, and then you're going to grab the wire. The grabbing wire direction will be the magnetic field. That means magnetic field going this way, coming back this way, and coming back this way around the wire. Important thing is this should be pointing upward direction. That's the current direction. If current going downward direction, you need to do the downward direction of the thumb, then grab the wire. That will be the clockwise direction current. So make sure that you follow that rule. That is, we call it as right hand rule, one of them. Okay. And same thing if you have a wire, right? If you have a loop of wire, I have a big loop. If I have a wire, then if current carrying in this direction, right? That means you see that it is, in my case, it is clockwise direction. So now you're going to take your finger and point into the clockwise direction. Then you're going to grab the wire. When you grab the wire, your magnetic field is going inside from this wire, right? Everywhere in this wire. So that's how the magnetic field create. And here you will see that your thumb is pointing this way, then you're going to grab the wire, then your other fingers going in this way. That is the magnetic field is, right? So now magnetic field is like feeling of your pulse, basically, right? So that magnetic field, that B that we are talking, will be able to measure by using Tesla. B units is a vector, units are Tesla. Okay. And so now you remember that after we talk about the electric field, we discussed the direction of electric field and electric force together. When you have electric field and electric force due to charged particle, those you can easily find because your electric force and electric field will be parallel or anti-parallel to each other, depend on the sign of the charge. But magnetic force is not that way. Magnetic force is totally different direction than the magnetic field direction, right? So there are two important thing in here, because you can have the, this is first case, you can have the current carrying wire inside the magnetic field, right? So you have a magnetic field created by using some magnets or big magnets, it doesn't matter. We'll say I have a magnetic field pointing in this direction, magnetic field B direction, everywhere in my screen, right? And then we'll say I have a current carrying wire inside magnetic field, but that will carry the current upward direction, right? So now this current and B together will create a force. That force we call it as magnetic force. Definitely force measured by using newtons, as we know, right? So now I will be able to calculate that force by using this formula. So I is the current of the wire that is inside the magnetic field. L is the length of the wire, and B is the magnetic field, and sine of theta. Theta is the angle between B and I. Okay, angle between B and I. Call it as the theta. In this case, it is actually 90 degrees. When it makes 90 degrees, your force is maximized because sine of 90 will be just 1. So that will create the magnetic maximum magnetic force. But let's practice the right-hand rule. This is another right-hand rule that you can use when you have a current carrying wire inside the magnetic field. Right? That wire will have a magnetic force. We're going to find it out which direction is. We definitely know how to calculate by plugging the value into this equation. So now direction again, when I show you the direction on my screen with respect to my right hand, you need to get the mirror image. So that's the hard part in video, okay? But practice it yourself. So I'm going to explain that. You have right hand, right? Take the right hand. So right hand, you can represent 3 directions. What are the 3 directions? This thumb will be one direction. Then I have 90 degrees in between thumb and my other fingers. So that will be your second direction. In addition to that, there is a third direction pointing out from your palm. So this will be my third direction, palm pointing out, right? So one direction, second direction, and pointing out direction from the palm, right? So now I have 3 things in here. I have I, B, and the F, right? So now in your fingers, you're going to label it. You cannot label as you want. This is restrict. You need to use exactly as it is. Your thumb of your hand will be the current direction. And fingers, these all 4 fingers will be the direction of magnetic field, this 4, right? And then your palm opening in this direction will be your force direction. That is the force direction, right? So now you need to practice it in your recitation session a little bit, this one, but we're going to do this single example. So now I have current direction upward. So now to make it current direction upward, you need to think the B direction and the current direction together. Now you need to keep the hand together by using current direction upward and your fingers towards B direction. Then your palm will be open into the screen, right? Current B, palm. So this opening is your force. So now, according to this diagram, my force direction will be pointing inward direction. That is the direction of the force. Okay, it is. You need to practice it a little more to get the direction. That's how we get the direction of the force. Totally different direction from the magnetic field. Okay. And again, by watching this equation, you guys know that when I increase, F going to increase, when L increase, F going to increase, and magnetic field increase, your magnetic force going to increase. So when theta is 90 degrees, it is maximum. Okay, so that's how the pose change. And also Tesla information is here. Sometimes we use the Gauss. Gauss is a small unit of the 10 to the -4 Tesla. Okay. Okay, so now second case. What is the first case is? First case, you're going to keep the wire inside the magnetic field. You have wire, you have magnetic field. Then this wire has the pose. That pose is the one that we discussed earlier. So now I don't have the wire. What I have is the charge particle. So now you have magnetic field and you have a charge particle moving, right? So now you're going to use again same right hand rule. But since I don't have the current this time, I have other all, but no current. But current actually a motion of the charge particle, as we know, right? So then you take the direction of your thumb to the direction of the velocity. If it is a positive particle, right? If it is a negative particle, that velocity should be opposite direction, but we'll start with the positive. So I have a positive particle moving in this direction, then that will be the velocity direction, and this will be the your magnetic field direction, then your palm will be open to the direction of the magnetic force. So now let's take this example. So now I have magnetic field inward and your particle is moving upward. So now what you're going to do is you're going to point your thumb into the direction of the velocity, but this is not what I need. My magnetic field is inward. So now your magnetic field inward, your thumb will be upward direction. Magnetic field inward and thumb is upward direction. Magnetic field inward, thumb is upward direction. Then your pose will create in the direction that I have to the left direction. Left direction. Although you see right direction on the screen in my picture, it is not correct because you see the image, right? So you see the mirror image, and this is my left direction. Okay, so now because of that, your pose will be to the left. Due to that reason, this particle will never keep the direction constant. It will keep making circular path because of this phenomena, right? That is the physics that we have in a lot of instruments like mass spectrometer, that you can decide which type of particle is that, right? Because of the direction of the bending of the particle motion and the particle accelerator and cyclone effect. So there are many applications on this phenomena, but that is coming from this part of the physics course. Okay. Again, when you have velocity or charge particle, then you will be able to calculate your magnetic force by using this exactly same equation I had earlier, but instead I and V, I and L, now I have Q and V. Q is the charge of the particle, V is the velocity, V is the magnetic field, theta is the angle between velocity and the V. Okay. Okay, so now when I have the current carrying wire, as I mentioned earlier, that wire can create the magnetic field. This is current carrying wire that can create the magnetic field. If you need to find the magnetic field here, that B in here will be equal to the mu naught. We call it as permeability. So I have that number in here, constant permeability and current of the wire, I. And you're going to divide by 2 pi and the distance from wire to your point of interest. Okay, so 1 over r way, the behavior will be 1 over r kind of shape. So that means when it go to the infinity distance, there is no magnetic field created because of this wire. Okay, so now next step is two wires. Right? If I have two wires that carry the current upward direction, there is two wires going to carry the current upward direction. So now according to the principle that we learned, this wire will create the magnetic field on this wire and this wire will create the magnetic field on this wire, right? So now if I have a current carrying upward in this wire, magnetic field will be pointing in this direction. Now this wire is sitting in the magnetic field is this way, current is upward. So now you're going to use your rule. This one is the rule, upward direction current, magnetic field this way, then this wire going to bend that way, right? So you apply the same rule for the other one, then if I have two wires carrying the current in the same direction, they're going to attract each other. That means these wires going to bend like attraction, because this will create the pulse this way and this will create the pulse this way. Okay, so similar to that, if you have opposite wires carry the current, they're going to bend outward direction. They are repel each other. Okay. Okay, so now we're going to move into induced EMF phenomena. Induced means there is no source, basically. This physics is coming from Faraday's law. After 200 years, 200 years before today, Faraday found a kind of like induce, or we can create the electricity without using power supply. So there is no power supply, but I can create the electricity. That is called it as induced voltage or induced electricity, right? So what that means, what he found is he did actually series of experiment. One experiment he did is this one. So he had the iron core, and then he created a circuit on the left side, as you can see it in here. And also he created the circuit on the right side, right? So, but you see that in right side circuit, I don't have power supply. This is a battery that is called it as power. That means I can produce the current on this loop, right? It will create the current. But the right side circuit, there is no any power supply. What I have is galvanometer. Galvanometer is the device that can see the deflection of the needle. That means if there is a current, it will deflect. If the current is negative, it will deflect into the other direction. That's the galvanometer. Galvanometer is the concept behind your voltmeter and the ammeter that you're going to use in your laboratory, right? But important thing what the Faraday discovered is, after he switched on this light, this circuit, he seen that this is deflected. This needle, I have it in the middle, deflect into one direction. And then he opened it. When he opened it, he see that this deflect into other direction. And then he keeps switch on the left circuit. Then there is no deflection. It is keeping exactly at the same place. So what he discovered is, by switch on and off in my left circuit, we can create the current on the right circuit. If I keep without changing anything, keep switch on or off longer time, nothing happened to the right circuit. That means there is something changing because of sudden switch on and off. That something happening is creating the induced electricity on the second circuit. Okay, that is what the Faraday found. And also he did the same experiment without even the power source by using the magnet. He had the coil again connecting to galvanometer, and then he tried to bring the north towards the coil, and then he see the deflection. And then he bring the north downward direction, and then he see the deflection in the other side, negative direction. And then he tried to keep it constant and no deflection. This is another experiment of that series set, right? So, but finally what he realized is there should be some relative motion that will affect to this kind of induced voltage. Okay, so now in this induced voltage is actually depend on the loop that you're going to keep. Do you going to keep your loop parallel to the magnetic field? We'll say I have magnetic field in this direction. You're going to keep the loop exactly parallel to the magnetic field, something like this. These are two parallel to each other, right? What that means is I have magnetic field this direction, but this loop is cross-sectional area is perpendicular to that. Then when I have this kind of loop, there is no magnetic flux. We call it as flux, magnetic flux. Similar to the electric flux, we have magnetic flux. Magnetic flux is defined as phi B, that will be equal to the magnetic field times cross-sectional area times the cosine angle in between B and A. That's how the value calculated. But we are not going that far. What we try to understand is magnetic flux that we call can be changed by changing B by changing cross-sectional area and by changing the angle between how you're going to keep this wire. Are you going to keep it this way? Then flux will be 0. If you keep this way, then your flux will be maximized, right? If you keep in some tilted angle, then you have greater value than 0. So that's how the flux going to be calculated. Okay. So now, after we know what is the magnetic flux is, that means how much magnetic field lines cross through this your loop. Then if you know how to calculate how much magnetic flux cross through the loop per unit time, then that is, we call it as induced EMF. Induced EMF. So right now, EMF, you can think it as a voltage. Okay. Induced voltage. Let's use the induced voltage instead of EMF. It can create the voltage because of the flux change, that we call it as induced voltage. So now this is rate of change of flux. And if you have n number of loops, if I have this coil, there are number of loops, not a single loop. And then you need to just times the number of loops from that value. But important thing is this negative sign. This sign is coming from, actually not from the Faraday. This sign, negative sign, is coming from Lenz. We are not going to discuss that part, but basically what the Lenz is saying that, I'm going to jump into next one and also jump to next one. Lenz is saying that if you try to induce some EMF, that induced EMF basically happening because the coil or the system that you have to induce in that case will create the opposite kind of magnetic flux. Simple example is, if I have a magnet, I know that this magnet will create the magnetic field lines, right? So now if I have a coil on the top of the magnet, then I know that this coil will create the induced current. That's the possibility that we discussed, right? Similar to that, I have a magnet and I try to bring it, then it will create the electric current or induced current in this one, right? So now when I do that, I know that north will create the magnetic field lines upward, but this coil will create a current to make that direction downward. So according to that, the coil will create the current to make opposite of what you are doing. Okay, that is what the Lenz saying. That's why there is a negative sign on that formula. Okay, so now we're going to discuss a little bit about back EMF and counter torque and eddy current, because those are the concepts coming from this induced information. And one thing that we know is, when there is a coil, when there is a current passing through the coil, because of the magnetic fields they will create, these coils will turning, right? So now this turn, sometime we need to turn back and forth to create generators. So to create the generators, we need to basically put kind of external force to rotate them backward direction, as we need the result to make it back and forth because of the or AC current that we can use that purpose, or we can use external magnetic magnets to make it opposite direction. That is called it as the counter torque or back EMF. And eddy current is something that when you have a kind of metal, if you have a kind of metal, if you try to bring a magnet on top, on inside this metal, so I cannot do it inside, but if I try to bring the magnet by touching or by close to this one, then we create a kind of magnetic field lines. Because of that magnetic field lines, it will create a circular loop on the metal piece. Those we call it as eddy current. What it does is when magnet move closer to the metal, this magnetic field, this magnet will create a kind of eddy current on this one. That eddy current will create the magnetic field to move this magnet slowly. So opposite direction, it will create the opposite magnetic field to slow down this motion, right? That is, we call it as the eddy current. So you have some information about the eddy current in here. They are circular kind of small kind of loops that will create throughout the metal. Okay. So I need to mention the application induction heating, and always you guys know that we have to find your video on your blackboard page, right? So there are videos that you guys can take a look in here. First one, so a couple of the electricity part is about magnetic forces. How we create. This is the video that I have for induction coil, because induction coil actually what is happening is you have coil, that coil have a current right this side. After the metal piece, you see that metal piece is not touching anywhere in the coil, but it will make a kind of heat. So that is actually we call it as induction heating. Now we have induction coils and induction ovens in our real life usage, right? Those coming from the physics concepts that you guys learn in this course. Okay, so that's what I have it in here about the induction heating by using eddy current. Okay. And last part will be basically transformers. Just need to explain basically what it is. We know that we have power plants, will create the voltage, then we distribute that voltage into homes and factories wherever we need it. But the power plants has the low voltage. You can make it high voltage by using transformers. Those we call it as step up transformers. That means you have basically one coil on the one side, other coil in the other side. Then if I have a power plant in this side, power plant, and then because of the secondary coil, you have many number of turns, then your voltage on the secondary coil going to be higher. So then you have high voltage, then you come to the home. When you come to the home, we don't want 200,000 volt. What we need is small voltage, right? So then we will reduce that voltage by doing exactly opposite, right? So now you're going to use this is the outlet coming to your home, and then it comes to the outlet, and this is your home. So it is exactly opposite. Then you make smaller number of turns, then it is called it as step down transformers. Then you can have a small voltage. Okay, so those how the transformers will work. Basically voltage ratio, you see that secondary voltage divided by primary voltage is equal to secondary number of turns divided by primary coil number of turns. It's always increase the secondary coil voltage if you have more turns. Okay, but the since energy is conserved, your power will be same. Power equal V times I, as we discussed in last section. So, but secondary coil voltage times secondary coil current should be equal to primary coil voltage times primary coil current. So, finally, important thing is your IS over IP ratio actually not similar to the voltage ratio, that will be opposite. Right? IS over IP ratio equal NP over NS. Voltage ratio was equal to NS over NP. Okay, go back in here, say NS over NP. And here I have NP over NS. Okay, keep those in your keep those in mind. Okay, so I will stop the today's session, and we have one more lecture that will be your last lecture.